Hi everyone, this is Shen Yi from Zhejiang University. Today I would like to introduce our work, Automated Unearthing of Dangerous Issue Reports. The coordinated vulnerability disclosure is commonly adopted by the open source society. Vulnerability disclosure is a coordinated effort between the reporter and the repository maintainer, which generally includes the following stages. Specifically, the initial report of a vulnerability is made privately, and the full details are only published once the maintainer is ready for the disclosure. CVD makes sure the maintainers have the chance and time to remediate. However, due to bad security practices, reporters violate the CVD by directly reporting the vulnerabilities through public issue reports while bypassing the maintainers. This poses huge security risks as now attackers can take advantages of the leaked vulnerability information to launch attacks when the OSS stakeholders are unprepared. Unearthing the dangerous issue reports at an early stage can help alleviate risks. For OSS users, they could start remediations earlier, and for ITS platforms, they could better manage the vulnerability reporting process. Here we present an example of dangerous issue report. This vulnerability allows an attacker to bypass the authentication mechanism of Greylog 2, a widely used OSS log management system. The vulnerability was publicly disclosed by NVD on July 17, 2020. According to the external references of the CV record, we retrieved the corresponding issue report, which was originally posted on April 24, 2019. The issue report described the details of the vulnerability, which according to CVD should not be publicly available until the official disclosure. Even worse, the maintainer let the issue report be publicly available for 450 days, leaving a large window for attackers to conduct zero-day attacks. Hence, such issue report is dangerous. With our preliminary study, we find that dangerous issue reports are common. We first collect nearly 4,000 CIRs. Here the CIR refers to the issue reports that are referred by CV records, and we use CIR as a proxy to operationalize dangerous issue reports. We find that 98.7% of CIRs are created before the disclosure of the corresponding CV records, and the associated vulnerabilities can pose huge security risks. We further investigate the challenges of identifying CIRs. We first try to use token-level keyword-based approach proposed by the previous work. However, we find that 17% of the CIRs are missed and a large amount of NCIRs are falsely achieved, which results in an extremely low precision. Besides, our dataset is highly imbalanced, and the limited CIR data belong to 132 vulnerability types with diverse causes and behaviors. This figure presents the cumulative distribution of number of CIRs belonging to the same CWE category. Nearly 80% of CWE categories have less than 30 CIRs. Thus, the vulnerability knowledge is insufficient and scattered. These two findings show that it is challenging for data-driven methods to learn effective vulnerability knowledge. Thus, we propose MemVul, which is composed of a matching module, a voting module, and an external memory. The memory component stores the vulnerability knowledge from CWE. The matching module matches the input issue report with each anchor in the external memory, and the voting module makes the final decision. We tackle the learning challenge by incorporating the external vulnerability knowledge from CWE and utilizing the Siamese architecture and a pre-trained language model. The motivation of incorporating CWE information is that CWE provides generalizable and representative vulnerability knowledge, and each anchor within the memory component corresponds to a specific vulnerability type. This table lists the attributes of CW entries used to build the external memory. We first used the attribute related weakness to organize the CW entries into a tree hierarchy, and then we used other 4 attributes to build each anchor. The matching module takes the target issue report and an anchor from the external memory as inputs, and outputs a normalized matching score indicating whether the input issue report describes the vulnerability type presented by the anchor. We implement the matching module using the Siamese architecture, which has two components, a shared bird encoder and a fully connected feed-forward module as the classifier. The voting module takes a list of matching scores as input, representing the matching degree of the input issue report with each vulnerability type, and outputs the final binary classification result. Next, we introduce the training details of the matching module. Since the issue reports are very different from the corpus used to pre-train BERT, we further pre-train it using the collected issue report corpus. For the training of Siamese architecture, we convert n samples into k times n sample pairs. Specifically, we convert each NCIR and CIR into k mismatched and matched pairs respectively. By transforming samples into sample pairs, we effectively enlarge the limited CIR samples. To tackle the extremely imbalanced dataset, we adopt the online negative sampling strategy, different from the common offline strategy where a balanced dataset is sampled first and used during the entire training process. Online negative sampling constructs a new dataset at the beginning of each training epoch with all CIRs and resampled NCIRs, which brings the following benefits. To build the experiment dataset, we first collect vulnerability relevant information, then we extract GitHub issue report links from the external references of the CV records and crawl all original issue reports of the associated GitHub projects. We include 3 types of baseline models, and for the evaluation metrics, except for precision record and F1 score, we also include 2 non-threshold sensitive metrics, AUROC and AUPRC, and the latter one is preferred on highly imbalanced datasets. With RQ1, we aim to evaluate the effectiveness of Manvo in identifying CIRs. Specifically, we consider a cross-project scenario that is identifying CIRs of OSS projects that are unseen during the training. Manvo achieves the best trade-off between precision and recall. Both precision and recall are important for real application scenarios since we do not want to miss any threats while avoiding too much false positives. We also present the precision recall curve to comprehensively compare the performance at different thresholds. Manvo achieves the best precision for recall above 0.4, and at recall of 0.8, Manvo improves the precision of the best performing baseline by 67%. RQ2 aims to investigate effectiveness of key designs of Manvo. The first and the most important one, incorporating the external vulnerability knowledge using the memory component, together with 2 training strategies. We experiment with 3 variants, each lacking 1 key design. The experiment results prove that all 3 designs are effective. We observed some false positives actually describe security information, but the associated vulnerabilities have not been reported to CVE. Thus, we conduct a user study to investigate usefulness of such NCIRs identified by Manvo, also the possible reasons why they are not referred by CVE records. We select the top 50 false positives and invite 5 security experts as our participants. For the first 2 questions, we ask the participants to verify if the issue report describes security information and whether Manvo achieves the related CW categories. Among the 50 false positives, 41 are confirmed by participants as security related, and in most cases, the relevant CW categories can be retrieved within the top 5 candidates. The results of these 2 questions verify the effectiveness of Manvo for identifying IRs with security information. For Q3 and Q4, we aim to examine the value of these security-related but not CV reference issue reports for OSS maintainers and users respectively. In Q3, we observed that 40 security-related false positives are considered to have higher priorities for maintainers, and in Q4, 28 are suggested to be publicly disclosed. We further explored the reasons of not publicly disclosing these security-related IRs via CVE. False positives not suggested to disclose, We observed the following 3 reasons for false positives suggested to disclose. 5 of them already have relevant artifacts referred by CVE. However, for the left 23 false positives, the reasons remain unknown. Hence, the identification of such NCIRs can also be valuable to OSS stakeholders, and we encourage future work to study the potential motivations that drive OSS maintainers to disclose certain vulnerabilities. Finally, Memware can help OSS users sense the emerging vulnerabilities in OS components used in their products and thus start the remediation process earlier. For IDS platforms, Memware can help them facilitate a better management of vulnerability disclosure process. IDS can integrate Memware as a feature that would warn users before posting the dangerous IR. They can also automatically move the existing dangerous IRs to the private channel. And that's all. Thanks for listening.